Searching for a friend's phone number in an extensive phone book can be done in two ways. You could start from the beginning and scan each name one by one until you find it. While this approach works, it could be time-consuming if your friend's name, such as Sarah, was listed towards the end. A faster way is to skip ahead to the section with names starting with S. This simple analogy reflects how search engines efficiently help to find information in the digital world. Searching algorithms are computing techniques for finding specific data within a larger data set. Searching algorithms are essential in today's digital world, where vast amounts of data are generated every day through activities like sending emails, posting on social media, and using cloud services. Finding a single file amid this sea of information, like locating one file on your computer without the search function, would be overwhelmingly time-consuming without efficient searching algorithms. Searching algorithms optimize this process by quickly and accurately identifying the required information, saving time and computer resources, such as storage, processing power, and memory. Several types of searching algorithms exist, such as linear search, binary search, jump search, exponential search, and interpolation search. Among these, linear and binary search stand out due to their simplicity and widespread use. In this video, you will learn about these two crucial searching algorithms. Let's get started. The linear search is the simplest type of searching algorithm. It's like starting at the beginning of the phone book and checking each name one by one until you find Sarah. In a linear search, the computer processes the data from beginning to end, comparing each item to the target item. For example, if you were searching for a number in a list of unsorted phone numbers, the linear search would start at the first number, compare it to your target, and move on to the next one if it's not a match. This process repeats until the number is found or the list ends. Linear search works best when dealing with small, unsorted data sets, or when data is arranged in a sequence that doesn't follow any order. It's often used when the data set is so small that sorting it or using complex algorithms isn't worth the overhead. It's also ideal when searching for specific items in a list, where the position of the item isn't known, like finding a name in an unordered contact list. Some of its advantages include being easy to implement and understand, working on any data structure, whether sorted or unsorted, and not requiring pre-processing or sorting, making it suitable for immediate searches. Its disadvantages include being slow on large datasets because it checks every element individually, and being inefficient with the time complexity of O of n, meaning the search time grows linearly with data size. In contrast, binary search is much faster, but requires sorting the data. Using the phone book analogy, it's like flipping directly to the section with names starting with S. Instead of checking each name one by one, you start in the middle of the book, roughly at the midpoint of the book based on the first alphabet of the name, and determine whether the name you're searching for comes before or after that midpoint. This way, you can eliminate half of the remaining names and focus on the relevant section. If Sarah's name is after the midpoint, you can immediately rule out the first half of the book from your search. You then repeat this process with the remaining half, selecting a new midpoint and deciding which half to search next. This method significantly reduces the number of comparisons needed to find the target by halving the search space at each step. The binary search is designed for sorted datasets. It's efficient in scenarios where data is already ordered or can be pre-sorted, like finding a word in a dictionary or looking up a number in a phone book. It's commonly used in algorithms where speed and large datasets are critical. A binary search is much faster than a linear search. While a linear search looks at every element one by one, a binary search has a time complexity of O, of log n, which means it repeatedly divides the dataset in half, narrowing down the search quickly. When used on sorted data, a binary search can narrow the target data in just a few steps, no matter how big the dataset is. However, there are some limitations to consider. First, the data must be sorted beforehand. If it isn't already sorted, that adds an extra step, slowing things down. Second, binary search only works with datasets that allow direct access, like arrays. It can't be used on unsorted or dynamically linked data structures. Understanding the fundamentals of searching algorithms, such as linear and binary search, can provide valuable insights into how computers operate behind the scenes to extract information quickly and efficiently. While linear search works well for small or unsorted data, binary search is the go-to strategy for efficiently handling large, sorted datasets. So, the next time you search for something on your computer or online, remember a well-designed algorithm is working behind the scenes to help you find exactly what you need as quickly as possible. Imagine this. You're at a garage sale with a table full of books, toys, clothes, and other goods. You're looking for a specific book to read. However, the objects on the table are not arranged in a particular order. How would you go about finding the book? The most basic technique is to begin at one end of the table and review each item individually until you discover the book you're looking for. This strategy, albeit simple, is precisely how a linear search works. A linear search is one of the most fundamental techniques for finding an item in a list or collection of data. The term linear refers to the fact that the search process proceeds in a straight line from the beginning to the end of the list. This approach doesn't require the list to be sorted and works with any type of data, such as numbers, words, and even objects. Let's break down the linear search algorithm step by step. First, the search starts at the beginning of the list. Then, the algorithm compares the current item in the list to the target value, the item you're searching for. If the current item matches the target value, the search is complete and the position of the item is returned. If the current item does not match the target value, the search moves on to the next item in the list. The process is repeated, comparing each item with the target value. Finally, if the search reaches the end of the list without finding the target value, it concludes that the item doesn't exist in the list. Let's demonstrate linear search using a Java example. You'll define an unsorted integer array of 6 numbers, specifically 3, 8, 1, 5, 9, and 2. The target number is 5. You'll write a class called linear search number example with the linear search method. This method takes an integer array and a target value to search for the target's index in the array. The target integer is searched inside the array and its index is returned. The linear search method is responsible for finding a target number in an array. The integer array represents the array of numbers you want to search, while the target integer is the number you are trying to find in the array. The for loop goes through each element in the array ARR. At each step, it checks if the current number, ARRI, equals the target number. If it finds the target, it immediately returns the index I, where the target is located in the array. If the loop finishes and the target isn't found, the method returns -1 to indicate that the number isn't in the array. Now back to the main method with an integer array of numbers and the target value. These two variables will be passed as arguments to the linear search method. Inside the method, define the unsorted array of numbers. The array numbers hold 6 different numbers. They are not in any particular order. Next, you define the target number that you want to search for. In this case, you're searching for the number 5 in the array. Then the program calls the linear search method to search for the target. This method returns the index of the target if it finds the number, or -1 if the number is not found. After the search, the result is stored in the variable result, and the program checks whether the target was found. If the result is -1, the program prints number not found. If the result is any other number, it prints the message number found at index, followed by the index where the target number was located in the array. Behind the scenes, the linear search algorithm would start by comparing 3 to 5. Since 3 is not equal to 5, it would move to the following number. Then, it compares 8 with 5. Again, they don't match, so it moves on. Next in the list, the linear search compares 1 with 5. There is still no match, so again it moves on. Now it compares the next number, 5, with the target value, 5. This time they match. The search is successful and the algorithm stops. The program's output now says number found at index 3. Let's summarize what you've just learned about a linear search. The dataset doesn't need sorting for the algorithm to work. The algorithm loops through the array by iterating over each element, comparing the current element with the target value. If a match is found, it returns the element's index. If it isn't found, the loop completes without finding the target and returns -1. In your example, if the target number of 5 isn't found, it indicates that the number isn't present. The time complexity of the linear search is O(n, O(n, O(n), where n is the number of elements in the array. So, when should you use a linear search? Use it when you have short lists or unsorted data. While it may not be the fastest approach, its simplicity makes it an excellent choice when ease of implementation takes precedence over speed. While a linear search is simple and easy to implement, it does have its drawbacks, especially with larger datasets. It is inefficient with large lists because it checks every item. If the list is long and the target item is near the end or not present, the search can take a lot of time. It's also not suitable for sorted data. If the data is sorted, use other search algorithms, like the binary search algorithm. The linear search, while basic, is a valuable tool for developers. It's easy to understand and implement, making it a great starting point for understanding search algorithms. By now, you're familiar with linear search and know it isn't the most suitable algorithm for long lists or large datasets. In this video, you'll explore the concept of temporal or time complexity, which refers to how the algorithm's running time scales with the size of the input data. In simpler terms, it measures how much longer a task will take as the task itself gets bigger. The time required for a linear search increases directly with the length of the list. as indicated by the formula O of n. The O means order of, and the n tells you how many items are in the list. For example, if the list contains 10 items, it might take up to 10 comparisons to find the desired item. Similarly, with 1,000 items, the search could take as many as 1,000 comparisons. To demonstrate how time complexity works in a linear search, write a Java class, linear search time complexity example. It will have a linear search method. It performs the search and counts how many comparisons are made. The method will return the maximum number of comparisons to find the target inside the array. Its parameters contain an int ARR, the array that is searched, and an int target, the number you're trying to find. Let's understand how this works. The int comparison equals 0 semicolon indicates the variable that keeps track of how many comparisons are made. The for loop goes through each element in the array. For each element, the comparisons ++ increases the comparison count by 1. The program checks if the current element equals the target number. If it finds the target, it returns the number of comparisons made so far. If the loop finishes and doesn't find the target, the method returns the total number of comparisons made during the search. Now, write the main method to set everything up. The program performs several actions. First, it creates 3 arrays of different sizes. The small array contains 10 numbers already filled with values. The medium array has 100 spaces that need numbers filled in. There's also a large array, 1,000 spaces, that also need filling. The program fills the medium and large arrays with values from 1 to 100 and 1 to 1,000 respectively. Each array element is filled with numbers in increasing order in these loops. The first loop fills the medium array, and the second loop fills the large array. The second action requires the program to set the target value being searched. In this case, it's 50, which is the number the program will search for in all 3 arrays. Finally, the program then calls the linear search method 3 times, once for each array, and prints how many comparisons it took to either find the target or finish searching the entire array. Let's break down what happens in each array. Suppose you have a list of 10 elements. In this example, the last number in the array is 10. So for the program to find the target value of 10, it would first check all 9 elements before finally finding the target at the 10th position. Now imagine a list with 100 elements. If you're searching for the number 100 at the end of the list, the linear search will check all 99 elements before it reaches the 100th one. Finally, consider a list with 1,000 elements. If you're searching for the number 1,000, the linear search will go through all 999 preceding elements before finding the target. For each search, the program prints out the number of comparisons needed to find the target or finish searching the entire array. The reason linear search is O of n is because, in the worst case, you might have to check every element in the list to find the one you're looking for, or to confirm that it's not in the list. This is a direct relationship. If the number of elements doubles, the maximum number of comparisons also doubles. Linear search is simple to construct and works well with small or unsorted lists. But because it has an O of n time complexity, the time it takes to search increases as the list grows. If you anticipate working with massive datasets, understanding the time complexity may lead you to investigate more efficient search algorithms, such as binary search, which has a time complexity of O of log n and scales considerably better with larger datasets. Knowing which algorithm to use and when comes with experience. You will soon learn which to use when given a scenario. Keep learning and growing your skills. Repeatedly finding specific data in large datasets is a common challenge. When those datasets are sorted, efficiency-minded developers rely on binary search algorithms to get the job done. In this video, you'll learn how binary search's divide and conquer approach makes searching sorted data a breeze. Binary search is an efficient algorithm to quickly find a target value in a sorted list or array. It does this by repeatedly halving the search space. If a target is smaller than the middle value, the search space is halved again. The process repeats, halving the search space until the target is found or the list is empty. If the target value is found, the algorithm returns its position in the list. If the search interval is exhausted and the target isn't found, the algorithm concludes the target is not in the list. Let's turn to Java now and see how binary search works with an example. For this demonstration, we'll create a Java class called binary search demo. It has 2 key parts, the main method, which starts the program, and the binary search method, which performs the search. The binary search method performs the actual binary search. The parameters here are int array r, the sorted array to search, and int target for the number to find. The method divides and eliminates sections of the array. The method uses 2 pointers. Left points to the start of the array and right to the end. A while loop continues checking the middle element and updating the pointers until the target is found or the search ends. The middle or mid index is calculated. If the middle element equals the target, the method returns the index mid. If not, it updates the left or right pointer and continues the search. If the target is greater than the value at the middle index, the program eliminates the left half and updates the left pointer to mid +1, continuing the search in the right half. If the target is smaller than the middle element, the program eliminates the right half and updates the right pointer to mid -1, continuing in the left half. If the while loop finishes without finding the target, meaning left has become greater than right, the method returns -1, indicating that the target number is not in the array. Next, write the main method that includes the array and target number. These two values are passed to the binary search method to find the target's index or determine it isn't in the array. Here is where you set up the array and the target number you want to search for. First, the array. This is a sorted array of integers from 2 to 99, meaning the numbers are arranged in increasing order. The fact that the array is sorted is important because binary search only works on sorted data. Let's say the target number is 23. The program calls the binary search method and passes the numbers array and the target number as arguments. The result will be the index position of the target in the array, or -1 if the target is not found. If the binary search method returns -1, it means the target number was not found in the array, and the program prints number not found. Otherwise, the program prints the index where the target number was found. What the binary search algorithm is doing here is quite simple. With the array and target number in mind, it's starting with the middle element, 45. And since 23 is smaller than 45, it focuses on the lower half of the array. Next, the middle element of the sublist is 7. Since 23 is greater than 7, focus on the upper half, so the third and fourth positions, 10 and 23. Finally, the search starts its next pass with the closest middle element, which is our target number, 23, at index 4. This approach to search isn't for unsorted lists, but for large sorted datasets, it's the most efficient. The time complexity of binary search is logarithmic, meaning the search time increases at a much slower rate compared to the size of the dataset. In other words, even as the dataset grows, binary search dramatically reduces the number of comparisons needed to find the target. For large-scale and high-performance applications, it's perfect. While binary search is ideal for large, sorted datasets, not all data is sorted or extensive. In such cases, a linear search becomes the more practical option for unsorted data. However, if sorting the data first is feasible, binary search can once again be the more efficient choice. Additionally, when working with more complex data structures, implementing binary search becomes significantly more challenging compared to the simplicity of linear search. For large sorted datasets, where searches need to be performed repeatedly and efficiently, binary search is the ideal choice. By halving the search space with each step, it significantly reduces the number of comparisons, making the process both faster and more effective. Binary search plays a key role in solving real-world challenges, from optimizing search engines to enhancing database queries. And now it's a valuable tool in your coding toolkit. I'm thinking of a number between 1 and 100. If I tell you whether your guess is higher or lower, what's the fastest way to find it? You could count up from 1 or down from 100, or guess randomly. But the most efficient way is to start in the middle, 50, and halve the options with each guess. This is how binary search works, quickly narrowing down possibilities. In this video, you'll learn how binary search uses this strategy and why its time complexity, O of log n, makes it so efficient for larger datasets. Time complexity helps explain how an algorithm's runtime changes as the input size grows. For binary search, the time complexity is O of log n, meaning that as the list gets larger, the time required to find an item increases much more slowly, following a logarithmic rate. Let's break down what O of log n means, with examples that show how binary search stays efficient as datasets grow. We'll use a Java class called binary search complexity, which is a method to calculate max comparisons. This method takes an integer and returns the O of log n value for that input. This method calculates the maximum number of comparisons binary search requires, depending on the size of the array n. In binary searches like this, each comparison eliminates half of the array. The number of comparisons depends on how many times the array can be halved. The formula math.log of n divided by math.log of 2 gives the base 2 logarithm, which shows how often you can split the array. For example, if the array has 8 elements, you can halve it 3 times. So, in the worst case, it would take 3 comparisons to find your target. Next, we'll write the main method, which creates an array with values 10, 100, and 1000. Each value is passed to the calculate max comparisons method, and the results are looped through. The main method sets up an array called sizes that contains the values 10, 100, and 1000. For each size, the number of comparisons required by binary search is calculated and the results are displayed. This for each loop goes through the array sizes 10, 100, and 1000 and calls calculate max comparisons for each. It will print the result for each value. For an array of size 10, binary search might require up to 4 comparisons. For size 100, it could take 7 comparisons, and for size 1000, up to 10 comparisons. Let's look at lists with 10, 100, and 1000 elements to further illustrate how binary search affects time complexity in practice. Take a sorted list with 10 elements. In the first comparison, check the middle element at the 5th position. Depending on whether the target is smaller or larger, look at the middle of the remaining halves, so either the 2nd or 8th position. Repeat this process, halving the list with each step until you find the target. In the worst case, how many steps will it take? The time complexity is O of log 10, or approximately 3.32. This means binary search will require about 3.32 steps to find the target in a list of 10 elements. Now consider a sorted list with 100 elements. Binary search will use the same method, but the number of comparisons, or passes, increases slightly because the list is larger. In the first comparison, check the middle element, the 50th position. Depending on the target value, check the middle of the remaining half, either the 25th or 75th position. Continue halving the list with each step until you find the target. The time complexity for this process is O of log 100, approximately O 6.64. So the worst case here will take 7 comparisons. What about a list that has 10 times as many elements? Once again, binary search keeps halving the list until it pinpoints the target value with minimal comparisons. With 1000 elements, the worst case is closer to 10 comparisons. Looking at lists of 10, 100, and 1000 elements shows how binary search scales with larger datasets. The magic of O of log n is that even as the list size grows dramatically, the number of comparisons increases very slowly. This makes binary search incredibly efficient, especially for large datasets. In this video, you learned how binary search's method of halving the search space drastically reduces the steps needed to find an element. The larger and more sorted the list, the more time-efficient binary search becomes. Oh, and the number I chose at the beginning? 42. The way a dataset is organized, whether sorted or unsorted, can drastically change how efficiently we can search through it. This is where the choice between linear search and binary search comes into play. In this video, we'll compare the performance of linear and binary search on sorted and unsorted data, and how the size of a dataset could influence your decision. Let's start with unsorted data, where the items are in no particular order, like randomly arranged books on a shelf. In this case, linear search is the only option. Why? Without any indexing, binary search has nothing to guide it. There's no way to divide the data in half, so each item must be checked one by one. In practice, the most effective choice would be a program like this, that starts with, say, a class called linear search books. Inside it, we have the linear search method and the main method. String books is the array of book titles you're searching through, and string target is the book title you're trying to find. The program uses a for loop to check each book in the array. It compares the current title with the target using the equals ignore case method, which ignores case differences, like whether Moby Dick starts with an upper or lowercase letter. If the target is found, the method returns its index in the array. If not, it returns -1, indicating the book wasn't found. The method will have a string array of books and a string target set to Moby Dick. Both will be passed as arguments to the linear search method. The program starts by creating an array of book titles, like a list of books on a shelf. It then searches through this list to find a specific one. If the target book is Moby Dick, it passes it to the linear search method. This line calls the linear search method passing the array and target title. It returns the book's index if found, or a -1 if it isn't. For unsorted data, linear search checks each item one by one. It's the default choice for smaller lists, but what about larger unsorted lists? Even with hundreds of unsorted books, linear search is the better option since binary search requires sorting. While binary search can start with unsorted data, linear search becomes inefficient with sorted data. To see binary search in action, let's switch to an alphabetically organized list of books. A binary search of sorted data like this might have a Java class called binary search books. Inside the class, the binary search method takes 2 arguments. Books is the sorted array of book titles, and target is the name of the book being searched for. in this case, Tolkien's classic The Hobbit. Using binary search, the algorithm starts by checking the middle of the list and then determines if The Hobbit is in the first or second half. It continues halving the list until it finds the target or confirms it's not there. To help you choose the right algorithm, let's summarize the best use cases for each. In general, for unsorted lists, linear search is the clear best option, since binary search requires the data to be sorted. But if the data is already sorted or can be sorted first, binary search is much faster. However, the size of the dataset does add some nuance to the choice. So, for small, unsorted datasets, like a few randomly arranged books, linear search is simple and effective. For large, unsorted datasets, linear search can still be used, but sorting the list first could save significant time on repeated lookups. That's because, for sorted lists, binary search is the clearer choice for efficiency. Although, if the dataset is very small, like an unsorted shopping list of 10 items, linear search may still be simpler and shouldn't be completely ruled out. Finally, for large, sorted datasets, binary search is the clear winner. Its method of halving the dataset with each step drastically reduces search time and makes it the most efficient choice. In this video, you've seen a comparison of linear and binary search, focusing on their efficiency in different scenarios. By understanding the dataset size and whether it's sorted or unsorted, you can make better decisions about which algorithm to use for optimal performance. Happy searching!